হ্যালো হ্যালো।
হ্যালো।
হ্যাঁ, কি খবর?
খবর এখন তোর?
কি করছিস?
এই তো বসে আছি
তুই কোথায় এখন? হোস্টেলে?
কৃষ্ণনগরে। না,
হ্যাঁ,
কৃষ্ণনগরে।
কৃষ্ণ। কবে গেলি?
এই তো কালকে আসলাম, বিয়ে ছিল, একটা বিয়ের নেমন্তন্ন।
ও, দারুণ তো। আমারও বিয়ে নেমন্তন্ন, আমার কালকে। এক
আমারও কালকে একটা আছে।
1 তারিখে ছিল বিয়ে নেমন্তন্ন, কালকে বৌভাত আর কি।
ও, আমাদেরও।
দুদিনই ছিল। একটা একটা হচ্ছে সোদপুর, আর একটা ছিল ইছাপুর।
ও, আমারও কালকে তিনটে ছিল।
ওটা চাইনি।
Hello.
Yes.
Hello. Yeah. Hi. So, yeah. So before I start today's lecture, so do you have any doubts, questions of anything that was done till now? So if not, today's lecture will be somewhat like a tutorial in some sense.
Sir,
Yeah. Go ahead.
sir, are we going to address the question in the last class about the longest increasing subsequence?
Oh yeah, no, that will be done in the tutorial.
Okay.
Tomorrow.
Okay. So actually, I had a doubt regarding that. So that will be clear tomorrow then.
Yeah.
Okay.
Okay. Yeah. So long as increasing subsequence, that will be done tomorrow. Okay. So today we will be doing two completely different problems, and I want you guys to solve it. Okay. So let me start with this thing. Can you see my class in this thing? Slides?
No, sir.
Oh no, sorry, I've not even shared. Yeah, can you see my screen now?
Yes, sir.
Yeah. So today we are going to talk about this edit distance. So one for the first problem that we look into is edit distance. So basically, so you have this two sequence of basically two string of two strings, and we want to convert one to the other. Okay, and these are the things that you are allowed to do. You can delete any bit you want, or bit or any position that you want. You can add a alphabet wherever you want to do, or you can change up. So say for example, so if the string is say snowy and we have sunny, then how will you do it? Right? So you can change these things in how will you do it?
3 steps.
In 3 steps. Okay,
Yes,
what
sir.
are the 3 steps? You
So
change
changing
them.
n. Yes, sir.
Changing n and all, right? Okay. So you can do it in slightly say lesser than that, or not lesser than that. You can do it in a different way. Say for example, I can delete u. So okay, the one that you told is that change u to n, change n to o, and change this last the second n to w, and it will change this to this, right?
So what are the available options or operations?
Yes, here.
Okay.
You're allowed to delete one, you're allowed to add one, you're allowed to change one. Every them of course same, cost one element each, one each. Okay. So you can of course change all of them, 1, 2, 3. You can also say you can delete u. Then what will you get? You will get s, n, and y. Then you can add a o in between two n's, and then change them. Right. So that is also something that you can do. So similarly, say here it is a bit more complicated one. So there is exponential and polynomial. How will you change it?
Sir,
Yeah.
sir, in the sunny to snowy case,
Yes.
I mean, the string one was snowy. So we have to do the edits in snowy, right?
Okay, it doesn't matter. It's both kind of similar things. Yeah, fine. You do the one in snowy. It's just the reverse of the other one.
So, but then won't we get a problem because we would want to delete both O and W to get N right before Y, and then add U and N.
No.
Oh, okay,
no.
sorry. Right.
I mean, when you convert one to the other, you have to. I mean, if I adding it, you have to delete it, and you have delete it to add it. It's the opposite of each other.
Okay, so just transpose. So it's reversible.
It's a kind of reversible. Yeah.
Okay.
Right. So yeah, what is the first string? What is the second string? Doesn't really matter that much. Okay. So similarly, we can talk about these two strings, right? Exponential and polynomial. Yes, I don't know what's there. Yeah. So basically, you want to change certain things. Like for example, let's see. Can you do something non-trivial? So I can say, for example, remove P, L, and Y. That will give you P, O, N, O, M, right? Yeah, so think about it. Okay, so what is the
Yes, sir. So I guess we can place the string one in an array, then find the largest common subsequence. Then in that string two, we will identify the indices of the longest common subsequence, and the other thing we can just delete and replace. And that would be, I guess, the optimal choice to us.
no, see, not exactly. They should be a bit careful over here. Okay, for example, you can have examples like this. Okay, so let me try to argue over here. I mean, you can have two different longest common subsequence, right?
Yes.
Yes, sir. Yes, sir.
And
So
they can be trashed in a way, so it's not very clear that you just always want to store keep one longest common subsequence intact.
yes, sir. So we want to minimize the deletion part. So we can, yes,
Yeah,
sir, somehow. So we
Right.
want to, because deletion and adding would be longer than the just changing thing.
changing it exactly, right? Exactly. You can't do as much as you possibly can. You want to change things, not delete and add. Right. So
Sir, can you please clarify what this edit distance is again?
okay, so say here, okay. So you are allowed. So I have this exponential and polynomial, right? My job is to say change this to this. Okay, so what all things can I do? So let me do this one. Okay, I first delete L, delete Y. Okay, so then I get PONOMIAL, right? Now I can, so let me, if I just use my trickery over here, I get this one and I can shift this to here. Now, what I can do, I can add E and X. Okay, so I get, so I've added these two things, E and X. Now what can I do? So now I know that there is something here that are same, these are same, and I want to change them, right? So one thing that I can do is that I can say change O to E. So this becomes E. N to N. So this becomes N. And then add T in between here. So how many operations have I done? I've done one operation, two, this is 3, 4, 5, 6, 7. So in this 7 operation, I have converted exponential to polynomial to exponential. So this is one form of editing that I could have done. I am allowed to add, delete, and change. Now there are other things that I could have done, right? For example, let me see if
we could have added
Yeah.
T in the step 6. Added N in the step 6.
Added.
Since the T is already no, it's fine.
Yeah. So maybe see. Let me see what could have done. Okay. Maybe if I write it again. Polynomial, right? Now the other thing that I could have done is I could have just deleted all of these terms 1, 2, 3, 4, 5, 6, 7 and added back all of this term 1, 2, 3, 4, 5, 6, 7, 8. I could have done that. Okay, or I could have just, maybe even simpler, I could have just simply changed each of them. I could have said change P to E, O to X, then again L to P. So basically I will change these things and I would have got E, X, P, O. Okay, not even N. A, X, P, O. Okay, don't change N to A because N is already changed, right? So in fact, I don't change N. Okay. So I would have changed Y to O, right? Then N I don't change. This was a O, right? Then again, this O, you change it to E, O to E, and N to N. Okay, so this becomes E and this is N. And now add T over here. Now, how many? 1, 2, 3, 4, 5, 6, 7. See, there is 7, another 7 changes. 7 changes through which I can change polynomial to exponential.
Sir,
Yeah.
so if we go back to how we dealt with sequences, so if I define a function, let's say OIJ, which basically represents.
No. Hold on. You are giving me the solution. Okay.
No, I'm trying to.
Yeah. You think about it yourself. Okay.
Okay.
Yeah. So just 1 second. Give me just 2 minutes for this. Okay. Yeah. So by the way, so the person who asked edit distance, is the edit distance clear now with example?
Yes,
Hello.
Yes,
Yeah.
sir.
So it is the smallest number of changes that you have to do to change one to the other. Okay. And again, I don't want to go into this. This is also applications and all are there. So this is the basic things that we have done. You have been given 2 strings. One string is A1 to AN and another string is B1 to BN. And your job is to make the changes to make the edits to change A1 to AN to B1 to BN. Your job is to do it in the least number of edits. Okay. Now, the question is, of course, given 2 strings, calculate the number of least number of edits that has to be done to change A1 to AN to B1 to BN. Okay. So is this problem clear? Hello.
Yes, sir.
Yes, sir.
It's clear.
Okay. Now I give you 3-4 minutes to think about how we want to solve it. Okay. Yeah. Everybody has to give me some solution, whether it is fast or small or slow, I don't care. Okay. Think about it and give me some solution.
So fast and slow, I didn't. So we have to find the minimum edits.
Yes, you have to
solution, right?
find a minute. You have to come give me an algorithm, right? Okay. So I'm not
Yes, sir.
saying that give me an efficient algorithm or something. Everybody has to give me some algorithm for now. Okay. I mean, you cannot say that.
I mean, the time complexity would be constant, right?
Constant.
I mean, because we are making a certain number of edits, and that number of edits should be same for every algorithm.
No. That is true. No. Okay. What is time complexity? Time complexity is the algorithm for finding that value.
Okay. Yes, sir. So there could be some other dynamic thing going on. Yes, sir.
I mean, this the answer will be same for both of for all things. Okay. So given a
Okay.
string A1 to N and B1 to BM. Okay. The number of edits that you need is minimum number of edits that you need is fixed.
Okay, sir. Yeah, yes, I thought that we are performing the.
No.
Yeah.
That is something I want the minimum. Okay. Now the algorithm for finding the minimum, I'm saying. Okay, that algorithm for finding the minimum, that algorithm, everybody has to give me some algorithm for that.
Sir,
Yeah.
first we identify the common string,
Okay.
and then because the common string is flagged, the other two strings must be different. So we now we have to just change them in that exact
How?
number of steps.
Is that the minimum? Will you get the minimum?
Because that is the number of characters which are different.
If, but they can be at two different sets completely, right?
Yes, then there is no common string, so we have to change the entire set. The number of changes, the smallest number of edits will be the smallest number of different characters in the two strings.
That is true. I mean, there'll at least be that many number of them, different characters. Maybe you can.
That will be exactly the number.
No. Think about it.
Sir.
Yeah.
So as I was pointing out, let us consider, let's say, let OIJ be the minimum edits required to.
Just can I stop you just once for a second? Sorry.
Yes, sir.
Yeah. So by the way, just to kind of say, what is the maximum size here?
N plus M.
It's N plus M, not N, not M, right? So the maximum number is not like, oh, this is an obvious algorithm that is there of order N or something. Okay, so the number of differences that you can have, right? That is how many? How many places where they can differ? That is at most the maximum of N and M, right? Hello? Is this clear?
Yes.
Yeah. So Rahul, you are saying, giving me this idea about how to approach it, right?
Yes, sir. It is very similar to things that
Yeah,
we have
exactly.
already done. So if I consider from A1 to AI and B1 to BJ, let us say OIJ represents the minimum number of operations required to convert the first string to the second. Now I have to just establish the relationship between OIJ.
Yeah,
OI
perfect.
plus
Yeah,
one.
I will stop you here. Okay, then let your friends try something. Okay.
Yes.
Yeah, you are completely right. Yeah. So I mean, so the greedy approach is exactly what you guys are saying. Okay, find the or the longest common subsequence, and that's it. That should do it. But that is not the case. Okay, let me try to give you with an example of this. So look at these two examples. This is string 1 and this is string 2. What is the longest common subsequence of these two?
FUN.
FUN. So if you want to skip this FUN, that means you're mapping F to F, U to U, and N to N. Then what will you do after that?
Delete B and add A.
Delete B and add A. What will be the cost?
So that would be 5 plus 4, 9.
9. Do you think 9 is the right answer here?
Sir, it is at most 7 because we can just change.
Exactly. It is at most 8 actually, right? You can change all of them bitwise and then delete one. So if you just delete them, So basically you can say that the edit distance okay can always be made to be less than max of a comma b n
Yes, sir.
comma n. But if you once you kind of restrict yourself by saying that okay I have to somehow store this longest common subsequence, you are really getting stuck. The reason is this because of the position of this longest common subsequence. They are not kind of correct in the right place in some sense. I mean, you can also say what happens if I just say bitwise. I kind of say this. They are. I want to look at the say number of. I want to say that I have to check the number of I such that AI is not equal to BI. What is this value? So it's a K. You say that oh okay the edit distance must be something related to K. It's something related to K. Say something. Actually, this is also not true. Why? I can give you an example, say A, B, A, B, A, B, and B, A, B, A, B, A, B, A, B, A. And these two strings are defined every place, but they are just off by just 2 points, right? The edit distance between this is just 2. Just delete A and add A here.
Yes, sir.
So did you guys get some algorithm?
So
Yeah.
So I was thinking of a graph to in a graph way.
Hmm.
So we know the maximum. What would be the? So we know all the edges. I mean all the alphabets involved.
Right.
So we can just make a graph of all the combinations and all the alphabets and just define the edges with the changes, elementary changes that we are doing, and just find the distance, minimum distance between the desired.
Okay, very good. So it's okay. So you are drawing a graph where the vertices corresponds to various strings.
Yes, sir.
So how many number of vertices are there then?
So that would be so if there are I mean so suppose there are k alphabets, so k to the power maximum of m comma n.
Okay. You are saying that you can draw a graph with the k to the power n n or m, the number of vertices, right?
Yes, sir.
And that's it, right? You are completely right. You can do that. There's no doubt about that. There's another way of thinking about it. You don't have to go to graphs for that. Okay. So I have this string. Sorry. I have this string, right? How many possible changes can I do? How many possible changes can I do?
So at each step we can do three
At each
many
step I can do not many,
steps.
right? I can do either delete, right? Or add, or
3 times maximum in command.
it's not 3 times. I mean, it's a more than 3 times in some sense, right? It's like, because I can do, I mean, this change a bit, I have completely, it's a, if there are if the number of symbols is k, then it is k times, right? K of possibilities. So I can delete or add or change to one of the other things. So there's k of them, right?
Do we consider change, or do we consider change as a
No.
deleted?
One change is a cost is one element, one cost only. Hello?
So then, but we can restrict the values that we can change to the values that are present in the destination string. So
Yes.
that can also be m.
That can
bounded
be
by
also be m also for that worst case, right?
Right.
But there can be some parameter in some sense. K you can think of. K can be m also. But say k is the total number of distinct alphabets in the second half, in second string, right? And all of the possibilities are I can add or delete, right? So maybe if I want to write it in this way. So I can, so say k is the number of distinct alphabets in B1 to Bn. Okay. Now I have A1 to An, and then I can have, what kind of actions can I have? I can do either I can delete, or I can add. Now what can I add? I can add any one of those elements, right? I can add any of the k alphabets, or I can change to any of the k alphabets.
Also, sir,
So total possible things are, say, something like 2k plus 1, right? Yeah, tell me.
yeah, okay, sir. So, okay, sir, I got it.
Right. And so every time, okay, so in fact, there can be some more actually. I mean, if you want to do the calculation, you can do a bit more careful calculations. But how many times can I do this thing? How many times will I do it? This action? How many steps? At most? See, we know that there is an upper bound of n plus m. Sorry, maximum of m and n, right?
Also, the deletion would be any of the
Yeah.
present.
So right. So I can. I mean, deletion is any of these ones present. Addition
that-
also is a addition at any of the places.
Yes, sir. So
And
that
change
would,
is also is any of the places. So yeah. So in some sense, you can say that this will be times m, or times n, say,
and yes, sir.
or m,
And-
or whatever. Yeah. So at most, I mean, I mean, we can almost say that we are never crossing m, right? But so the total number of we can look at, consider all the possible changes that could have happened, that can happen, all the possible set of edits that can happen, but the number of edits is less than max of n plus m, right? N and m. So how many possible things are there? It is this 2k plus 1 times m whole to the power, say, m. I mean, just without loss of generality, let's assume m is bigger than, right? And that's it. So this is the total number of possible edits that you can have. So it's an exponential number of possible edits. You can see which of the edits are working and which of them are not, and then find out the one which is the minimum. So if you are interested in the worst, in the kind of just an algorithm, this is a very simple algorithm. You don't have to go to graphs or something. Basically, consider all possible sequence of edits. Of course, you have to assume that the number of edits can never be more than n, maximum of n and m. Okay. Yeah. So the possible number of edits can be unlimited, but you can upper bound it, okay, by saying that, okay, the total number of edits, since the total number of edits cannot be, or the minimum must be less than maximum of n comma m. So we will only look at all the possible sequences of edits where the number of edits is less than maximum of n plus n comma m. Right. So that's an exponential number, something of this form. You go over all of them and you find it. So that's perfectly fine. But the problem is that this is an exponential time algorithm, because the total number of possible things, which is a brute force algorithm, right? Anurag, is it fine?
Yes, sir. Yes, sir. So in the graph thing, we were also doing basically the same thing.
The graph thing, you are doing basically the same thing.
Yes, sir.
Yeah, but now question is that, can you do better than exponential? So how many of you have got a polynomial time algorithm? Can you just maybe raise your hand or something like that? Do something on this. How many of you have got the polynomial time algorithm? Or how many of you have got an algorithm that is not exponential? What happened? Nobody is responding? Rahul, you had one, right?
Yes, sir. Yes, sir. I had one.
Yeah. So what about the rest? Aniket?
Sir, I'm thinking about the parameterization of AI and BJ.
Okay.
And what if they are equal, then it's trivial. Then it's just if you define that function as ed of I comma j, which is the edit distance in the first I characters of the first string and the first j characters of the second string.
Correct.
Then if AI is bj, if they're equal, then it's simply the same as ed of I minus 1 comma j minus 1.
Right.
And but if they're not equal, I'm trying to actually provide an algorithm with the proof of correctness that so can we claim something like this, that if one string, if we have string 1 and string 2, and we take a substring of string 1 and a substring of string 2, so let's call them ss1 and ss2, then ss1 and ss2 will have edit distance lesser than equal to the edit distance of string 1 and string 2.
You can say that. That's the true valid statement. But yeah, that is true. But
Actually, proving that is a bit difficult, right?
no, I don't think proving is difficult, but I don't see why you need that, whether it is smaller or lesser. See, you want to do it in a recursive form. Okay, as I told you, if that think recursively.
Right. Okay.
Think recursively.
So the only step that we need to think about is what happens if AI is not equal to BJ, right? How do we think about it in terms of EDI
Right.
minus 1 comma j or something like that?
Yes.
So okay, let's suppose if AI is not equal to BJ, then
okay, let's think about it this way. Don't think in that direction. Okay.
Okay.
So say that you have these two strings. Okay, you have two strings. Say one of them is, say, as I told you, right, exponential and polynomial. Now, these first two strings are different, right? First two letters are different. Then,
yes, sir.
But at the end of the day, this P should kind of, I mean, the first position to be replaced by E.
So there has to be some transformation in some sense.
So what kind of transformations can happen?
It's just changing, or we can maybe remove P and hope that one of the letters later comes back and is an E itself.
Yeah, exactly. So that's the three possibilities are there. One is change P to E. Okay, that's one possibility. In that case, if you change P to E, right? In that case, I should not be worrying about these two things at all. Again, done.
Okay. Right.
Right? These two are done. All I have to change is this polynomial to this part.
Right.
Right? Good. Now, if that is not the case, okay, so if that is not the case, then what happens? I can delete P. By delete P, what happens?
Then we are looking at a
This
transformation
case
from
disappears.
right.
And then you change polynomial into exponential.
Right.
That's it. Right. And you pay one more extra part. Right. Okay.
Yes, sir.
Now, what is the third option?
We have to delete E.
So third option is that, so I have to do something with P, right? But I don't do anything with P. So maybe this P finally gets pushed here or later on somewhere. Okay.
Right.
So E gets inserted. Insert E.
Right.
So I get insert E over here. And in that case, I should not be looking at this part any longer.
Okay.
I should change then polynomial to this exponential without the E.
Right. Right.
So these are the three things that you can do.
Okay. Right. 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 So yeah, this gives us all the three steps that we have to consider. It's just the minimum of so edi comma j becomes equal to edi minus 1 comma j minus 1 plus 1 if ai is equal to bj, and it is the minimum of edi minus 1 comma j, edi comma j minus 1, and edi minus 1 comma j minus 1 whole thing plus 1 if ai is not equal to bj.
Correct. So what about the rest of you? Chandramouli, is it fine? Okay, maybe he's not there. Arunabo? Arunabo, are you there?
Sir.
Yeah.
So okay, so I see how we are doing this, but I don't. So how are we choosing the minimum thing?
How are we choosing the minimum thing? We are not choosing the minimum thing. We are using it recursively.
So we are just checking all the possibilities.
We are checking all the possibilities. Okay.
Okay, sir.
So it's basically say if you want to find out the cost of whatever, say cauliflower in the market. Okay, how much cost is of the cauliflower that you can get. Now, of course, there can be a market next door to you. You can just go and check it there, but there might be markets far off, right? So how do you do it? You kind of say that, sorry. You kind of say that, okay, I am here, okay, I want to check the cost of cauliflower. I am asking a friend of mine, okay, first friend, hey, in your locality, what's the cost of cauliflower? So he says something X, X1. Hello, okay, but then I have to go and get it from you. The cost is C1. So the cost that I pay if I get it from your place is C1 plus X1. Okay, then you ask some other friend, what is the cost of cauliflower in your place? He says, oh, X2. And you know the cost of getting it is C2. Then you ask some other friend, what is the cost of the cauliflower at your place? It's X3 and C3. And similarly for other friend, right? Now, what is this friend saying? So this friend C3 or so C1, he is not saying that what is the cost of cauliflower in his neighborhood. He is saying that this is the amount of cost by which I have managed to get the cauliflower. Right. So which means that he has done his own homework. He has possibly used lots of other small things to solve his problem. So this is an algorithm sitting here. It is solving that algorithm for some other setting. You are using, so he has done his work. And once he has done his work, you can say that, okay, once you have done your work, I can use your work to find out how much cost will it take for me to get it. It is C1 plus the cost with which you have got. So in some sense, instead, you could have gone to his place and all the other places and everywhere and checked, right? But you have kind of given this work, split this work into various friends of yours and asked him to solve it. And now, once they have answered back, you can find out the cost of for your case. This is the same thing that happens here. If EDIJ is if I want to change is the smallest number of sequence required to change A1 to AI and B1 to BJ, the idea is that, okay, forget it, that if the last bit is the same, so here, if the last bit is same, Y is same, then it says that, okay, so then one option is to just say that you just keep this Y and change this to variables, SNOW, snow to SUNN. But that is what your friend is doing, which is, sorry, ED44. Now, when you have come to this next step, N and W, then what all things can you do? You can say that, okay, so this is what you can do, right? This is what I have told you. I have to say, check, I want to change SNOW to SUNN. Either I can change W to N, that's one case. In that case, I will ask my friend ED33 to say what is the cost of changing SNO to SUN. And my cost will be this plus 1. Right?
Yes, I got it.
Now, the other option is that I don't change it, but I delete. So this is change W to N. Now I can also delete W. If I delete W, then this W disappears. And all I ask is that, okay, I'm asking now a friend. See, I have deleted W and I want to change SNO to SUNN. So 3, 4. And then also I have to pay the extra cost of deleting. And the other one is that I insert N. Okay. If I insert N, then I have to replace SNOW to SUN. So it is ED 4,3.
Sir, could you repeat this insertion thing?
Yes. So see, I mean, at the end of the day, the last thing, right? It is SNOW, the W has to go down to N, right? So last thing has to become N somehow. Okay. So there's few things that we can do. We can change W to N, then it changes last one to N. Or I can remove W for now on, which means that maybe later on I will do something else, but for now I can remove W. But now therefore my value becomes small. So the same cost is changing SNO to SUNN.
That's the deletion part, right?
This is the deletion part.
Yes, sir. Okay, sir. This was fine.
Yeah,
So
the insertion, but the other thing that I can do is I don't do anything to W. And instead I add an N over here. Okay, if I add an N over here, then the last bit is N.
Right.
Right. So all now I have to do is to change SNOW to SUN.
Okay.
So that is ED 4,3.
Yes.
Right. And these are the only possibilities that are there that you could have done. Right. So what is ED? So we wanted ED 4,4. What is ED 4,4? It is the minimum over all of them,
Yes. Sir.
and that's it. Right. So it is the minimum over all of this. Okay.
Hello.
Yeah, hello.
Sir, were you calling me or Urunavu that time? I heard it Urunavu, so I did not respond.
No, I called you also, and then I called Runavu, both of you.
Oh, okay, sir. There were some issues.
Neither of you responded. So,
I was there the whole time.
okay.
I just heard Urunavu's name. My name was skipped somehow.
Okay. Okay, so basically the recursive algorithm is this, right? Now let me ask you one by one, maybe that would be useful. How many of you actually have done it? I know I can see 3-4 people who are answering continuously to me. Like for the Arunavo, where are you? Are you there? I guess he is not there. Okay. Chandramouli, did you manage to solve it?
Sir, I understood this, what you have said.
But you could not do it by yourself.
No, sir. I was thinking some different idea, but I was thinking in this way that means suppose I fixed the number of changes, edits is k, and then I run a loop on the k.
Yeah, you can do that. You can fix the number k and you ask whether it can be done. But then also it will be a
then the time complexity. I think so. This one is better.
There it will be actually exponential. I don't think it can be better than log polynomial. Okay, but you can try it out and try to convince yourself. So who is this person? Class?
Some people are doing from the class, it seems.
Oh, some people are doing from the class. Okay, very good. How many of you are doing from the class?
Only one person.
Only one person is doing from the class. Okay. So did you do? So what's your name?
Sujatapa.
Oh, Sujatapa. Okay. So now, so could you do this?
No. No, I could not.
You could not do that. Is it clear now?
Yes, it's clear.
Okay, because I'm going to give you another question right after this. Okay, so that you have to do. That's why I'm asking you guys one by one. So Dhruva Nandi?
Yes, sir.
Could you follow? Did you follow this thing?
Yes, sir. I understood this.
Did you? Were you there in the last class?
Yes, sir. I attended the last class.
Okay, so but that last class also we did something similar to this about LCS.
Yes, sir.
Okay, fine. Let's go ahead. Jyotishka Roy Chaudhary?
Yes, sir.
Yes, sir, meaning what?
I mean, I could not solve this by myself. I understood everything, but could not solve this by myself.
Okay. I mean, I can tell you this one. This is the kind of a small, trick for everybody of you. Think recursively. Again, I can tell it, okay? Think recursively. You want to use, a recursive algorithm is always a good idea to start everything, any algorithm, okay? Think whether you can break it up into smaller problems and solve it. So, Ritobrata Karmakar?
Yes, sir, I have understood this, but could not figure out by myself.
You could not figure it out. Okay. Well, sister.
Sir, in general, how to know where to start from? I mean,
Always. Okay. So, there's a natural tendency that I saw here today also with many of you. The natural tendency was to solve in a greedy way. Okay. So the first thing that you guys were trying is, okay, let's find the largest common subsequence and do it. Okay. Now these are all greedy techniques. Now greedy techniques are not bad, but they have to be proved, and the proofs are very complicated and sometimes they're not true. Okay. For example, here the greedy algorithm is not true. Okay. So instead, if you think of it algorithmically, the best way of starting it is always try to say that how can I make this problem smaller? Okay, so for example, here, like if somebody comes up and tells me that, oh, okay, you can say, yeah, right, that I know how to change SUNN to SNOW in the shortest, smallest possible way, then can I solve it? Okay, I mean, of course, I mean, seeing it in hindsight is easier. Okay, but in some sense, you have to think in this way that somehow you have, how do you take help from a subroutine that has solved the problem for a smaller instance? Okay, so this is almost similar to, analogous to the induction proofs in mathematics that you have seen.
Right, right.
Okay, I mean, induction also is not a very natural way of thinking about it, but it works beautifully, right?
Yes.
Same thing here. Okay, so let me go to the next problem then. Okay, so by the way, I have not solved it. Okay, this is recursive algorithm. Now, what do you do after that? What is the runtime of this?
So we can do this dynamically, just as we did in the LCS question.
Right. So if you solve it, if you solve this runtime, okay. So see, this is, if I say the I plus j is n, right? So then t of n equals 2. You have to solve it in 3 times, right?
Right.
Plus 1. So it is something like this: 2 times tn minus 1 plus tn minus 2. Now
Right.
this is a bad runtime. If you solve it, you realize that this will end up becoming exponential.
Right.
But at the same time, the issue is that here I have this ij. The total number of this edij's is at most n times m, or n plus 1 times n plus 1, right? Because
Right.
I is between 0 and n, j is between 0 and m. So you kind of store it. Use dynamic programming to store this whole problem. Same thing here. So see, here you have Sunny. You can write down this whole thing here. Write down this whole thing here. What I want, so this is matrix for edij. I am interested in this part. Right? Now
Right.
let's look at this way. Ij, okay?
So, sir, can you please show us the recursion once again? The final recursion. Okay, sir.
Okay. So edij depends on either I minus 1, j minus 1, or I minus 1, j minus 1, I minus 1, j, and I and j minus 1. So here in the picture, so this term, this part, or any quantity here, sorry, not this. So anything here, you can see my cursor, right?
Yes.
Yes, sir.
This square depends on what? This square can depend on, if these two strings are same, then depends on the I minus 1, j minus 1. So this diagonally, this top left corner, right? Or if they're not same, then it is I minus 1 j, which is the left corner, or I j minus 1, which is the top corner, or this corner, right? So it
Yes.
depends upon this 3.
Yes.
So now think of it filling it up. How can you fill it up? Can you fill it up this one right now? Of course not, because I don't know any of this. Right? I have to start from somewhere. But the best part to start is that, do we know these 2 lines? And of course,
Yes,
I know. I know that if I have nothing, then I have to produce S. I have to add S. Right?
Right.
Similarly, if I have SUNNY, I have to add all of the SUNNY, so it will be 5. And similarly, this thing over here, if I have SNOWY and I have to make it into an empty string, I have no other option but to delete all of them. So I have got these 2, and now I can start filling up. I can fill this one up. Yes, I can fill this one up. If these 2 are same, then this is just the previous one. Sorry.
Sure. So this is actually a distance, right? In terms of,
This is a distance.
this is a metric in the sense that
Yeah.
follows the triangle
Yes,
inequality and all
yes,
those
yes,
kinds
it
of-
does. It does. It is a metric. Yeah.
Because it is, after all, a distance in a graph,
Right.
where the graph was defined by the neighboring.
Right. It's a
changes.
distance. Yeah.
So this is actually a metric space where it gives a metric space structure to the set of all strings, and
Right.
the distance of any string from the zero string, the null string, is the number of
Right.
characters it has.
Right.
And also the distance among any two strings of the same number of characters is also k itself and not 2k. In the normal sense, in the regular sense, it will be 2k, but
Yeah.
here it is bounded by k itself.
Yeah, it's bounded by k. Yeah.
So
That's
it's
true.
in some sort of sense a very compact metric space.
Yes. Yeah, this is a metric. So there are lots of metrics on the strings. Okay, there's a quite a lot of metric that you can define, or we define on this space of all strings.
Okay.
Any distance is of course one of them, but there are many more.
Right.
So for example, here, say we can now start filling up right here. So this one is what? This, since S and S is same, it must be 0. So 0 here. Then, okay, why don't you guys solve it actually? Maybe you can do it.
So
Right.
SS is, so should we do it on our own? Like,
Yeah, you can do that on your own and tell me what you get here.
okay. So that's a long
Sir,
computation.
the first unfilled row will be 0, 3, 2, 5.
0,
3, 2, 5, 4.
3.
0, 2, 3, 5, 4, I guess. Oh, no.
0, 2, no, it's not 2.
No, sir, 0, 3, 0, 3.
Why 3?
Sir, because 2 and 0 are not equal, and sorry.
0 will propagate.
Minimum of, right? So
It'll be 1.
1, right? 1. Sorry.
Because look at this one, right? So the I
Yes,
minus, yeah, so it will be 0. Then this will be the minimum. This will be minimum of all of these things added plus 1, right?
Right.
So it will be 1. It will be 2, 3, 4.
Yes, sir.
Okay. Now this one will be 1.
Right. No, so this will be 2.
Oh,
Oh, okay.
zero,
Yeah,
This will be 1. Well, this is
It will be
0.
one.
So it will be 1.
Right.
Right. So 1. Then this will be 2. Now what is this?
2.
This will also be 2 because this one is actually 2.
So won't that be 1 right before it?
Oh, this is 1. So this is the 1. Right. That's true. Oh, this is 1.
Oh,
Why?
1.
So, yeah, this will be 1 as well, because
Oh, yeah, this is 0. Right.
0. Right.
See, I mean, it's not easy to compute this whole thing even by looking at this string, right? But I mean, filling it up is not hard actually.
Right. Yes, sir.
Yes, sir.
Anyway, so I sure you can fill up a matrix from this. Okay.
Yes, sir.
So basically what we did was we came up with the recursion and then we solved this. Okay. Now, okay, so this what is the runtime of this? This is of the string, this whole space is of size n cross m, and every point is costing us how much time?
Order 1.
It's just a constant number of times, right? I'm looking at all the 3, I'm looking at, and that's it. So it's a constant number of steps. So it's ordered n times m. Okay.
Yes.
Again, remember the trick. Think recursively.
Sir.
Yeah.
Sir, I have a question.
Yeah.
So for such problems of such kind, is it possible to establish lower bounds?
No, not easy actually. No. First of all, see, it's it's not a very easy job to find a lower bound here. In fact, there are a lot of things where I mean, it's dynamic programming is a one way of coming up with a good upper bound, but that doesn't mean that it is the best way.
Yes, sir. We have come up like with a significant like polynomial time upper bound.
Right.
So, but can we say something about the lower bound also? Like in
not
like let's say either in definitely not in general, but let's say a problem of like this editing distances or something. Yeah,
no.
Finding. Okay.
No. I mean, they're very. So first of all, you should remember that these lower bound problems, okay, lower bound things, there are very few problems which has lower bound ideas. Okay.
Yeah.
And in fact,
so,
I mean,
I was thinking in this case because it is like we have fixed number of operations, and each time, we are like doing changing a bit, like can we have some form of decision tree? I don't know. I'm not sure. I was thinking, I'm not convinced. So I was asking you.
Yeah, no,
So-
I mean, I don't think so. I mean, I see what you are coming from, but I don't think this will give you anything much. But you can think about it. Okay. Can you have a see? Of course, order n plus m is a natural lower bound, right?
Yes, sir.
Now, why is it order nm? Can you prove that you cannot do better than even n plus m log n plus m? Yeah, it'll be very good. Actually, very interesting to see.
So we'll have to look at the graph, right? We need some sort of structure.
You need some
To
sort of
think of.
structure. Yeah.
So the graph structure might help the metric distance.
Right. Okay, I think we will see some more interesting things of this direction. Okay, about this lower bound also very soon. So let me go to a new problem. Okay. So maybe I'll just stop here. Yeah. So here is this problem. It's called the knapsack problem. Maybe many of you might have heard of it also. Okay. So I have a collection of items. Okay. Now each item has two parameters. One is a volume, another is a cost. Okay. And now I want to store these objects in a big sack or container. Okay. Now I know that that sack has a volume of C. Okay, that bag has a volume of C. Now I want to pack as many number of things as I can to this sack. But what is it? What are the two important constraints, or two are the most important constraints? That the amount, the sum of the volume of the objects that I have selected or put in the bag, that must be less than C. Right? They have to be contained in that bag. And at the same time, I want to take away the items which are most costly to me. So the sum of the cost of the items that go into the bag, I want to maximize that.
This seems like a simple Lagrange multiplier kind of problem.
Okay.
So because suppose the volumes that we are choosing for, say, the items x1 to say xn, those are say v1 up to vn.
Yes.
And their cost per unit volume may be ci. So that will be, so the total cost.
You are not allowed to pick fractions.
Okay.
So
You're not.
what is the origin of this problem? I mean,
this is a very important problem. Okay, this is a very, 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 very important problem. I will tell you what. Okay, so for example, a company has a certain amount of money. Okay, and they want to. So this is the amount of money that they want to invest for advertisement. Okay, now they can either advertise in, say, radio, and the cost is something, and they have a certain amount of people can reach out to through the radio. They can put an ad in a newspaper that will cost him something, but the total number of people they can reach out to is also something. They can put an ad in an IPL during an IPL match in a TV. That's a very costly thing, but they can also reach out to a lot of people. Right? So at the end of the day, they can invest in a lot of these various things. But under the condition that the total amount of money they spend on various of these advertisement things, that is less than the total amount of budget that they have. At the same time, they want to maximize the number of people they reach out to. That's knapsack problem.
Sir, Sir, so we are. So what are we exactly outputting? Like we have to give a sequence of items. Like
yes.
Like
you have to give the list of items. Okay. You have to give a list of items such that the cost of them is less than, the volume of them, sum of the volume of them is less than C. Okay. and the cost and among the all possible things, the cost is maximum.
So, sir, what did you say that it cannot be fractional? The
You
volume?
cannot. So you have an ad, and that ad will cost you 5 lakh rupees. You cannot say I will give half a ad. You have to take that ad or not.
Sir, sorry.
Yeah.
Sir, so can I attempt a solution? Like I'm thinking.
Yeah. Go ahead.
So I was thinking that so we have a bag, like imagine a bag,
right?
And that has volume C, right? And I have to fill it with some items. So if I think of like shortening the problem, then we can divide it like again in the subsequence problem we did it that we can do like let us pick any arbitrary item. So we have only two cases if that item is in the bag or not.
Right.
So let us say if that item is in the bag, then we have a subproblem with a reduced volume and a reduced reduced volume, right?
Right.
And if that item is not, then amongst the n-1 items we have to attempt a FC problem. Like if I call the FC.
That is true. What you told is completely correct. Okay. There's only one.
But I don't know how. Okay.
Yeah. There's only one catch to this one. There's just one idea left from your things. Okay. Or how to get this one into polynomial. Okay.
I mean, is the general direction?
General direction is correct.
Okay, so this kind of partitioning we can do, right?
Something like that, yeah.
Okay.
Sir,
yeah.
I was asking, we have this list of items and every item's volume and cost is given. So can we choose multiple number of the same item?
No. There is one item of every item.
Okay.
There's one item, one quantity of every item. Yeah. Okay, so I have some very
So there's no point in considering like unit volume, those kind of things are not.
No, nothing. None of them are useful. Yeah. See, these things. So this is where I think this whole concept of discrete and continuous world changes. Okay, this problem in the world of continuous is very easy, as one of you pointed out, that the Lagrange multiplier now. Okay. But
so then if it's a continuous problem, then we don't even need to consider a Lagrange multiplier problem.
Yeah, nothing. It's a simple things will do.
We can just simply look at the quantity with the minimum, the maximum cost per volume, and then just use that item alone.
As much as you can, and then use something else. Yeah.
Right.
Yes.
But that may not exhaust the whole.
Yeah, but then you do the next one.
Yeah.
Okay. Sir, I didn't understand. Like Aniket, like what was he saying? What were you saying? Sir, what was he saying? Sir,
no. Sir. Yeah, go ahead, Aniket.
Yeah, I was saying in the continuous problem, in the problem where we can choose a fraction or just a scalar multiple of any item in our to choose in our bag, then we can just look at what is the maximum cost per volume item, and we can just keep on filling that up in our bag as long as we can. Once we've exhausted that, we can look at the next item with the maximum cost per volume and then keep filling it up and so on. So we don't have to do any Lagrange multiplier or anything of that sort.
Right.
I think, yes.
But here the main issue is that first that it is a discrete set. So you cannot take partial quantities of it. Okay. And this really makes this problem much harder. In fact, we will come to this problem again and again a few times after this. Okay. So yeah, so this is the problem, right? So I have these items, item 1 to n, volumes of v1 to vn, cost is c1 to en. Pick some set of items such that summation of vi is less than c, and your job is to maximize this quantity. Okay. Now, let me see. Yeah, so as I told you that this problem is very hard. I will come to that later on, not in this time, but later, but in couple of weeks time, we will come to see that how hard this problem is. But yeah, so as I told you, okay, maybe if you guys want to, so I think Rahul has managed to already solve something. So I would like again give you guys another couple of minutes or 3-4 minutes to actually try to solve it. Okay, come up with an algorithm to solve it. And Rahul, if you have got this, whatever you told is correct, but now you try to write a
Yes, sir. That is
algorithm.
Yes, sir. That is what I'm trying. I'm trying to formulate it like mathematics.
Yeah, right.
Sir, the complication is in the how do we discretize the cost?
Right. So very good. How do you discretize the cost, right? So for now, you can say that, let's say that this capacity of the bag, okay?
Yes,
Let's put a
domain restriction.
Yeah. Domain, yeah, kind of a domain restriction you can think of, yeah. Okay, think of this one. That think of the C1 to Cn are all think of that. Okay, so think of V1 to Vn and C1 to Cn are all integers, and this capital C is also an integer. Okay, you solve it for that. So assume that this all the volumes and all the cost, all of them are integers, and the back capacity is also integer.
Sir, so if our function that we want to find a recursion for, let's call it k for knapsack, k of c comma j, right? That is, or something like k of c comma I is a parameterization, which gives us the where I is items 1 through I. If we're considering only items 1 through I, we can call it the problem k c comma I. So the recursion that we're trying to or the recursion that was proposed was k c comma I is minimum of k c comma or sorry so what okay
maximum.
So actually k gives us the list of items, right?
You can for now say this sum of the values. Let's think of it.
So the sum of the cost.
Sum of the cost, yeah.
Okay, right. So it's the maximum of k c comma I minus 1 and k of c comma or k of c minus ci comma I minus 1, right?
Yeah. So good. So say, I mean, basically what you are saying is that, which I think Rahul also said earlier, that if T is the set of items, okay?
Right.
So T is some subset of item 1, item 2, till n, right? And if I say that, okay, the knapsack problem of C comma T is the maximum cost of storing. So this is the, just 1 second. Sorry, yeah. So say K C comma T is the maximum value of items from T that can be stored or whatever put in a sack of size C. Okay, so this is the amount. I mean, if the sack size is C, then what is the maximum value that I can take? Right? And then what I can take is that I can take any item, say item I from T. Then you can always write that K C comma T. There's only two possibilities, right? One item is that I have picked up that item. If I pick up that item, I have cost a cost of CI C1 plus, then I've already put it up in the sack. Then the sack's item, sack's allowed volume has gone down by V1, right? And I have left with this set T minus C. So this is one option that I can do. Or I can say, look, I'm, yeah.
T minus I, right?
No, T minus I, sorry. T minus I.
The case is outputting the cost.
Case is outputting the cost. For now, let's think of the cost. You can also output the actual value, actual size of the actual items, list of items. But let's just first try to output the test value. Okay. Now, what is the other thing that I could have taken? I could have not picked up CI. But in that case, my job will be just to fill up as much as I can with T minus I. Right? So max over these two is what I have. Correct?
Yes, sir.
Yes, sir.
Okay. Now, problem is that if you write it this way, what is this I? Who is picking up this I? Any I, some I. So I have to kind of solve this problem for a lot of things. What all things do I have to solve? I have to solve this case C comma T for different values of C and all possible C subset of the item. Right?
If we sort the items in the order of their cost, so will that help by any chance?
That will of course help. Then what happens? See, let's see this way. Okay, so let's just first sort the items as I1 to IN. Okay, and now case I comma C is the cost, maximum cost of item that can be packed in the capacity C, but the items are, meaning the set T that I talked about, was this capital I1 to capital I. So the items are just 1 to I, not any arbitrary set, subset.
Sir, we sorted the items just
in some
randomly, right?
order, doesn't matter what.
No, order will not. Oh, achha. So we can build tables.
We just enumerated them.
You just enumerated them, yes.
Okay.
So this will work now. We can build tables. No?
Now we can build tables, right? So again, you can very well see that case 0 C is 0, case 1 0 is 0. There's no non-trivial thing here. If the size of the stack is 0, then nothing much I can do. If I don't have any item, then nothing much I can do. Right? And for all of the other things, I comma C, it is I minus 1 comma C, and it is I minus 1 comma or I minus 1 comma C minus VI plus CI. The exact thing that we just now talked about here.
Yes, sir.
Right. And that's it. So for example, here, I have this say items and snack. So how big is the table that has to be done? And we can go back and see. If I have to solve it in a DP form, how big the seed that I have to solve? Table that I have to fill up.
So the I parameters will definitely go from 1 to n.
Yes.
But the C parameter doesn't have to go through every integer from 1 to C.
That we don't know. It might not go for every integer, but even if you don't think about it that non-trivially,
Okay.
it is at most 0 to C.
Okay, right.
Right. So this table size is therefore C plus 1 times n plus 1. Right.
Yes.
You 0 to n, and that's what you do. And this is what you have to do. Now see, look at this one. This is actually very interesting. What is the value here? Till now we told that okay, a value here just matters about all the previous ones. Right?
Right.
It is true here. What does this value imply? This value useful for? This value, yeah.
Right. So since its cost is 2, sorry, the cost is 4, right?
4. Okay, maybe let's think of this way. We'll
volume.
further. Yeah, so it's 2 9. Okay. Yeah. So cost is 4. No, cost is not 4. What is 4?
So the
What
volume
is
is
the
9.
volume is the
Sir,
4.
yes.
Right? Yeah, volume is 4, right?
Yes, sir.
So if I take it, I have to look at it as if I take it, then it would be, I have to, instead of 9, I have to go to 9 minus 4, which is 5 and 1.
Okay. Right.
Here, could you please repeat this?
So here is it. Sorry. Maybe this is okay. So maybe I should copy.
This is fine. But I mean, how are you counting this?
How are I counting this? So what is
no, sir. I mean, how are you filling up this table?
exactly? So what is here? What is this one? What is KSI? Okay. So KS say 2, 9. What is this quantity?
It will be maximum of case 1 9 comma
1 9, right?
yes, sir.
Comma
1
KS 1 comma. So C was 10. Say if C is 10, right? It is 10 minus the V2 plus C1. So maybe if I do it like this, you can see this thing. Right?
yes.
Yes, sir. Yes, sir. Sir, so
Now,
what we
yeah.
have is something of the form of C minus summation of VIs or something of that form.
yes. So if a 2 9, here I is VI is 4, V2 is 4.
Right. So
Right?
1 5.
So this will be 1 5. So no, this is 9. This will be 1 5, right?
Yes, sir.
KS 1 5 plus something plus
Right.
whatever 10 or something that was there. Right.
So the value right above, and in that row we have to go back
Yes.
VI.
So it will be the value right above and this one.
Right.
So it is no longer the next door neighbors kind of stuff, but some value. But more importantly, the values are this cell depends on 2 cells. one cell is on top of it in some place, and the other cell is either in top or left. So it's in the third quadrant in some sense, or second quadrant, right?
Right. Actually, we don't even need it to be before us, right? We can always say that any value is dependent only on its previous row. So we can fill
Yes.
it row by row.
Right, that's also true. It's only depends upon the previous row items. That's true. Good point. So if I fill it up therefore row by row, I will be able to fill up the whole string.
Yes, sir.
Yes.
And I think this discretization has some group structure, right? We can think of it some sort of a
That you can do. I mean, you can look at all the, instead of C, you can look at all the points that are generated by this,
the generation of the VIs.
Of these VIs. Yeah, you can do that.
Right.
Yeah.
Okay.
So is this problem clear? This one, what we did?
Yes, sir. Yes, sir.
Everybody is clear with everybody?
Yes, sir.
But
Sion,
sir,
Paul? Yeah, go ahead.
sir, if the volumes were real numbers and if there were a lot of
Right.
items, then this will blow up. I mean,
This will blow up. See, that is the blowing up is the one part, but there's a more interesting part to this whole thing. Okay. Okay. What is
Sir,
the cost?
actually,
Yeah.
the sub problem. I'm saying by blowing up, I mean I have to solve. Let's say if I have to solve an infinite number of sub problems to solve a higher problem, then there is no point of DP. Like the point of DP will be lost.
That's true. Yes.
So, but if we use this discretization, the span sort of thing, then it doesn't blow up. It actually only depends on the number of items.
Yeah, but
Yes,
the
sir.
span can be huge.
So, but it has a bound, right? It has
It is a
which
bound,
is-
but we are talking about these discrete points, right? It's a 2 to the power n. Think of it.
Okay. Yes. 2 to the power n. Right. It is an exponential bound, but it is still finite. We can reduce it to a finite DP problem.
It's a finite, but it's still exponential.
Right.
Right.
Yes, sir.
Yeah. By the way, the same thing can be done in the other direction also. Okay. So
maybe better than
If
the. Sorry.
yeah.
Yes, so I was just saying, if we just scale everything up and just, if we are giving.
Yeah. So you can always think of it, then you can scale up and all. Okay. So we will come to that. Okay. So there are lots of things that can be done. Okay. Like there are the approximate versions and all those things are there.
So we are only dealing with the rational numbers. So we can always scale up to the natural numbers. Yes.
Yeah. But okay, so what is the cost of this whole thing algorithm? Let's think of it. What is how much is the time complexity of this algorithm is? So the time complexity, we filled up this whole matrix, right? How big was the matrix? This matrix was n times c.
Yes, sir.
Right. So this runtime is order c n times c. Right?
Yes, sir.
Good. Now question is that is this polynomial or exponential? See, I have been using these words polynomial and exponential kind of in a bit of a vague way for quite some time.
Sir, again, the very same problem. Sir, C, if we think input size as number of bits to be specified,
Right, very good point.
Then it will again.
So what is the input size? Input size is you have given the C. So if I want to say, I have a knapsack of a size 10,000, right? Then how many bits do I use to solve it, to represent it? I just gave C equals to 10,000, right? So the input size is I have written C equals to 1 0 0 0 0, right? So 5, just 5 digits I have used.
Yes, sir.
So input has only size 5. Input size is only 5 digits. But how
Yes.
big is C? C is 10,000. That
Right.
is not 5. Okay.
Right.
So the input sizes are log C plus everything else has been written in the binary value or some value, right? I'm not saying that it's log 2, maybe log 10 also, but something of the form, right?
So even here in such a case, even though the C is an integer, we would not
Yeah.
want to consider every single place. It will probably better if we do an order n times 2 to the power n algorithm in that case.
So in some sense, this is not a polytime algorithm. When we say an algorithm is polynomial time, we mean it's a polynomial in the input size. I don't remember if I have used this term earlier, but whenever we say an algorithm is polytime algorithm, okay, or polynomial time algorithm, this means that the time complexity or number of steps, this is same as the number of steps, this is upper bounded by polynomial, okay, some polynomial, some fixed polynomial in the input size. This is something that was very crucial. We have used this word linear and all those things in the case of graphs. Why? Because the graph was given as an adjacency matrix, then it has a size n squared. If it is given as a adjacency list, size v plus e. So linear accordingly is defined as v plus e or v square, right? Here
Yes.
also, input size matters. Okay.
So we never want the user to input a value, and we are like having a space complexity of that order itself, which is the value that was inputted.
I mean, that would be what is we would like to do, right?
Right. Right.
I mean, think of it yourselves, right? I have just given you my size of my budget is 10 crore.
Right.
Okay. How many bits do I need to represent 10 crore? 8 digits.
8 digits. Right.
Okay. Now, if you want to solve this problem, you have to produce me a table whose length is how much? 10 crore.
Just 10 crores.
Crore.
Right.
Yes, sir.
So what we want to do is whatever input we have, we do some mathematical operations on it, but not actually use that number as a.
Yeah. We don't want to write something with that number.
Right. Right.
I mean, it's a massively big problem thing. Okay. By the way, this whole concept is what is used in things like cryptography and all of that. Okay.
Okay.
Yeah. I mean, so
Yes,
all
sir.
your yeah.
So if we don't have the indices from before, we cannot really say anything about the.
Yeah, if you don't have the indices from before, or particularly forget indices from before, but unless this C is a very small number, okay, this quantity C is very small, we are not going to do much. Okay, if the C is small compared to this quantity, then yeah, okay, we are fine, right? But if the C is if this capital C, the size of the knapsack, the actual size is quite a lot, and this algorithm is not a polytime algorithm.
Okay, sir.
Okay. So this is not good enough for us, although we did a very nice job with this dynamic programming stuff. Okay, just one second. Hello. Yeah.
Yes, sir.
So, okay, so let me just kind of say it here. So this problem is what is called, we will come to this, it's called the NP-hard problem. We will come to that quantity later on. So this problem is something for which we don't believe there is an exponential polynomial time algorithm.
We don't believe.
Yeah, and I will give you why. Okay, so this is a very beautiful part of this algorithms thing, something that no other mathematics subjects has this kind of a thing. Okay, we have a very interesting. So we have a famous. So I don't know. So you guys coming from this mathematics or statistics world, right? You have heard of this Clay Math Awards, the Clay Math problem.
So P versus NP problem is one of the problems.
Yes. So this
The
problem.
millennium problem.
Yes. So this Clay problems. One of them is P versus NP. Okay. So if you
So
solve.
what does it say? What does it say?
I'll come to that. I'll come to that. Basically, in short, I can say that what we can say is the following. Okay. And I will prove that later on. But is that P is equal to NP if and only if this knapsack problem has a polynomial time algorithm.
Oh.
And this knapsack is not the only problem.
What do we mean by P is equal to NP?
You know what is P?
Yes, I mean the problems that can be solved using.
Yeah. So again, I mean, there we will be doing things more formally in the course. Okay.
So is it loosely saying that there is a strict classification of any problem? Either it can be solved in polynomial time or non-polynomial time, and there doesn't exist such a classification if this knapsack problem can be solved in polynomial time. Then everything can be solved in polynomial time or something like that.
No, not that. Okay, so it's not about polynomial. So okay. So let me tell you the NP problem. Okay. Now
Okay.
this what is an NP?
So I remember an example.
Okay, tell me an example.
So for Sudoku, there are two kind of algorithm that we can work with. So
Right.
first is if we are given a solution and we have to verify if the solution is correct.
Right.
And the other thing is we have to find the solution.
Yes, exactly. So these are the two problems. So you are completely right. So basically, NP is non-deterministic polynomial time. Okay, it is the collection of problems for which the solution can be verified in polynomial time.
Okay.
Okay. Now I will again. I don't want to do P. I mean, whatever I'm going to say now in this class, don't. If you don't follow it, no problem. I will come to that later on also. Okay. So there is this whole class of problems for which solution can be verified in polynomial time, and then there are problems for which the solution can be found in polynomial time. The question is that are these two sets equal? Meaning set of problems for which a solution can be verified in polynomial time is same as the set of problems for which can be found in polynomial time.
Right.
So that is what is P and NP. P is equal to NP problem states.
How is this? How are these sets well defined?
Or which set will define?
These sets, the set of problems for which there exists.
Okay, so I have to. Okay, so what is the problem? Okay.
So
What is the problem? Okay. So one way of defining what is the problem is, okay, I don't really want to go into it today, but
essentially the notion is that associated with every single problem is a time complexity, right? It's saying that every problem is characterizable.
Yeah, every problem has a best time complexity. That's no doubt about that.
And so, sir, if we've attached a time complexity not to an algorithm but to a problem itself,
yes,
then the set of problems who have polynomial time solutions is already well defined, right?
That is, yeah. So, but okay, I think he's asking something more basic. What do you mean by a problem? What's the set?
Yes, sir. Yes.
Yeah. So okay, what is the problem? Okay, so first of all, let's talk about what is called Boolean problems, okay, or decision problems. Okay, so all of these things are what we talk about as decision problems. Decision problems are problems for which you have an input and the output is either 0 or 1. Okay. For example, okay, I give you an input, say the knapsack instance, okay. Just now what we are discussing, instance, and I give you a value k, and I ask, is there a solution for knapsack, or is the maximum, or is the best solution for knapsack, for that knapsack problem, correct? Sack problem or instance is bigger than or equal to k. Or in other words, say I can say that, okay, here is the instance, right? This is a problem. Where is the problem gone? Here, this is a problem. Okay. Now, is the you're trying to optimize, maximize the
Equal to hello.
Yeah. Go ahead.
So the final statement that you have written there, won't it be less than equal to k? So the final statement that you have written just before.
Doesn't matter equal to or not. You can define it in either way.
Okay. Yes. Right.
Okay. Irrespective of them, both of them are well defined.
Yes, because the complement of the question is just need to find the means above
Same thing.
the price.
Same
and
thing.
yes,
It's not a big deal. It's just a one step here and there. Okay. We are talking about the preciseness of definition. Okay. So, but this problem is a decision problem. Okay. So what we have solved till now, the knapsack problem, or finding the edit distance, minimum edit distance, or finding the longest length of the longest common subsequence, these are what is called as optimization problems. Meaning you are trying to optimize something. You optimize the amount of edits required to send one string to the other. You are trying to optimize the length of the common sequence between two strings. You're trying to optimize the amount of cost of item that I can pack in a knapsack. Okay, your job is to find the optimal solution. And the decision problem is that, is there a solution which achieves something bigger than this value? Or is there a solution that achieves something lesser than this value? Okay, so you can see that these two are related to each other. I have not formally defined it, that how are this knapsack problem and this decision version of these problems are related to each other. But you can see this one somewhat. Hello.
Yes,
sir.
Yeah.
Hello.
Yeah.
Yes, sir.
Good. So now these inputs, then I can talk about an input of some string, right? So I can talk about input of 0, 1 to the star, some, right? So it's an input which is of some string encoded in some way, right? Or if I don't want to use 0, 1 to the star, I don't care. You think of it as some alphabet to the power star. Are you comfortable with this notation of sigma to the star?
In what context?
I mean, do you know what is this quantity?
No, sir.
This is the union of I equals to 1 to infinity sigma to the power I.
Sigma is some matrix.
What?
The sigma is what? Yeah.
What is sigma? Sigma is some alphabet.
Some alphabet.
Yeah. So some finite set. It's a finite set. So you can forget that. So think of 0, 1 to the n. So what is 0, 1 to the power 5? What is this?
Like 0, 1 cross 0, 1. This.
So it's a binary string of.
Yeah, binary string of length 5.
5. Okay, good. So this is the binary string of length, some binary string. So it is the union over I equals to 1 to infinity, 0, 1 to the power I.
So this is just capital N.
This is just capital
N. This represents all natural numbers.
If you think of the codes as if you think of 0, 1 as representing representing, so see, these are like different from natural numbers. Okay, for example, 0, 0, 0, 1 is different from 0, 1 here.
So this is actually more representative of the real numbers then, right?
This is not representation of reals or naturals. These are strings of length or zero is binary strings. The set of all binary strings.
Different lengths, right? All possible lengths.
Yes, set of all binary strings is this quantity.
Right, but then I'm talking about the cardinality. It's the same as the real numbers. Okay?
This is same as the
Same as real numbers, why?
Because we can map it to the like a binary number. No? The same argument that we used to prove that 2 to the power Aleph naught is Aleph 1. It's the same thing.
This is not it. This is countable. Think about it.
This is countable, right? Yeah.
This is countable.
So, but then can't we map some binary string to a unique real number using firstly we can just talk about some
Binary
real
string
number
to a
as-
unique real number, but that not be the opposite direction.
So, but then if we can find a unique real number for oh, okay. So, but then
Think about it.
if
Think
we
about
can
it.
just
Yeah.
okay, okay,
Okay, let's not go into that. We're taking a diversion completely.
okay, right.
Okay, let's not go into that. Okay. Now, if I take any sigma, sigma is a finite set, say A, B, C. Okay. Then what is sigma to the power n? Now, sigma to the power 5. It is the set of all strings of length 5 containing A, B, and C. Right?
Right.
Similarly, you can define sigma to the power star. So in some sense, if sigma is all the alphabets in the English dictionary, A to Z and some other numbers, space and whatnot, then sigma to the power star is a set of all English text that you can write.
Yes, sir.
Okay. So you can think of that this input is therefore mapping from sigma to the power star to 0, 1, but sigma is some, I mean, you can think of it as 0, 1 if you want. If you really want to think of it, you can think of it as 0, 1 to the power star to 0, 1.
So we are talking in terms of a general problem, not the knapsack. Like we are
No,
not
just general.
just a decision problem. We have some decision problem, and
yes,
and you're defining a domain of input.
Right.
And
So
with a decision.
Any decision problem.
Yes, sir. Yes, sir. I get it. There is
Any
a domain.
decision problem is a map from 0, 1 to the star to 0, 1.
Oh, yes, sir.
Okay.
This is okay.
So how can I define it? Okay. So this is one way, or another way of defining it is what we call as, so if this is an F, another way of defining it is considered F inverse 1. Right? So this is a subset of 0, 1 to the star.
Right.
Yes, sir. Yes.
So usually a problem is defined as this. Okay, so when we say a problem, it's basically talking about a problem. It is a set of problems for which your set of inputs for which the algorithm should output 1. Okay, so this is called a language. Okay, one way of thinking of it is that sigma star is the set of all possible English, I mean, all possible sentences that you can write in English, right? They can be garbage, gibberish. You don't know. But a language is the set of all valid, understandable English sentences. Okay, so the language is a subset of sigma star. Okay, that is how this whole thing is defined. So any problem, when I say that I have a problem P, that problem is that it is a subset of, you can think of 0, 1 to the n, a star. And the question, and what is the question that we want? I want is, I'll give an instance. What is an instance? A particular instance, meaning I have to tell you an example, right? I will, for example, in the knapsack case, I will tell you the size of the knapsack and the volumes and all those things, right? And what is the K and all. So its instance is, and I will give you an X in 0, 1 to the star. And the question is X in P? Or not P, I should not use P at all. Yeah, P should be a dangerous thing to use, L. X in L. So this is a kind of problem. So any problem that we solve is represented like this. Okay.
So all problems are decision problems.
Yes. So whenever we talk about this kind of classification, we talk about decision problems. All decision problems are written like this. Okay.
So you're talking about decision problems alone, right? This is like
yes, just decision problems. Just decision problems.
Okay. Right.
Okay. Now, what is P? P is the set of problems. Now you are comfortable with set of problems. So what is a set of problems? Meaning, in some sense, I can write this is a L subset of 0, 1 to the star, such that there exists an algorithm A for all x, A of x comma L. Okay.
X belongs to where? X belongs to.
What is x belongs to? For all x, okay. Let's see what does x belongs to.
Okay. It's fine. X
belongs to 0, 1 to the n star.
Yeah.
So for all x, okay, this algorithm AXL equals to 1 if and only if x is in L, and this more importantly, A has time complexity polynomial in size of x. Okay, now what do you mean by polynomial in size of x? I can define it even further. I mean, that's a more complicated thing to kind of define, but I can do it. Is that so? Okay, maybe for you guys, I can define it. Okay, let's see. Okay, and a polynomial P such that for all x, okay, the A has time complexity less than P of size of x. Is this fine now?
Yes.
Yes.
Okay, it is formally defined.
So,
Sir, is the knapsack problem a
decision problem? No, it is not. But if you add an extra condition that, okay, I'm going to give you another value, say T, and I ask it, is the maximum value of knapsack more than T or less than T?
Okay.
That's a knapsack problem. That's a decision problem.
Okay.
And now you can kind of convince yourself. So think about it and try to convince yourself that these two problems, so solving the knapsack problem and solving the decision problem of the knapsack problem, are basically same.
Okay. Right. Okay.
I mean, one of them you might have to do a binary search a little bit, and other of them you.
So why are these two same?
What is the same?
So just what you said right now. That
why are the same?
this problem and the knapsack problem is.
Think about it. Think of it in this way, okay? That if you have a friend who comes up and tells me that, okay, give me a knapsack problem and a knapsack instance and a T, whatever the value is T, I will answer you correctly whether the knapsack problem's maximum value is more than T or less than T. Okay, can you use your friend to solve your problem, knapsack problem?
Yes, we can do so.
We can do a binary search.
Yes, you can do with a binary search. Yeah, think about it. Yeah. So basically it will be off by a little bit, but that's not by a polynomial factor only.
Right.
Okay. So anyway, so I'm not going to go any further today, but this is P, the set of all polynomial. This is the set of all. This is we call as polynomial space, polynomial time. So okay, the class P is this. Okay, now we can also define the class NP. Okay, and we will do it in the maybe okay. Since we have started it, I will do it in the next class only. Okay,
Sir,
and we
can you at least please define this NP for now?
Again, the formal definition will take some time. Okay, if I define it, it will take. I have to explain you why am I doing what. But basic idea is that these are the set of languages for which I can give you a quick proof, or you can verify correctness. So, for example, right? You have a friend, right? And he kind of tells that, okay, give me a knapsack problem instance and a T, I will tell you whether it is less than T or more than T. Okay, he answers something. Now, can you verify it? Whether he or she is actually lying to you or solving it correctly?
Sure, but wouldn't that just be
Same as solving the problem.
Solving
Yeah.
the problem, because here
it is not. Okay, now you can insist that a friend gives you some more information. See, it's a friend's job to kind of convince you. Okay, so in some sense, the friend says that yes, the knapsack problem is more than T. Then what will he say? He says, okay, these are the set of items that you choose.
Okay, right.
Okay, and using that extra information, you can solve it. See, this
Okay,
is
sure.
same as what I face in my or any teacher faces. Okay, we can we can give you an exam problem. Okay, whether I know how to solve it or not doesn't matter. You are supposed to solve it and write the solution. If you give a solution, I should be able to verify the correctness of the solution.
Right.
And that's it. I don't have to know how to solve it. Maybe I have no idea how to solve it. But you
Okay.
gave me a solution, I have to verify it.
Okay.
So question is that who are more powerful? A person who is just able to verify a solution, or a person who can find a solution?
Actually, the person who has solved it has already verified it as well.
Yes.
Makes sense.
But question exactly. So this is actually this philosophically, this problem is there even in the world of philosophy. Okay. Verification and solution, are they as hard as each other or not? Okay. Anyway, formally, whatever it is, I will tell you in next class.
So if you were to try and read some of this up on our own, would it be digestible in this sense?
Yeah.
Sense
Many of them are digestible. Most of them are digestible. You can even look up the Wikipedia page for this thing. P versus NP and all those things are. See, of course, some of the things that is written there are kind of maybe wrong or something like that. Okay, and will not give you the right perspective, but you will be able to follow quite a bit of it.
Sir, hello.
Yeah.
Sir, why are we using 0-1 star instead of sigma star?
We can use sigma star.
I mean, sigma star.
It doesn't matter, both the same.
Language, because language will be everything that we can say, so it's sigma star, right?
Again, but at the end of the day, also, if you have a finite language, right?
Okay, so we can.
You can also represent it in 0 and 1. Right. So it doesn't matter to some level. So a finite sigma and the 0, 1, basically they are same.
So in this case, the problem and the x belonging to L all determines all corresponds to whether we can write it down in language, right?
X is in L means that whether that instance, okay,
The valid language.
is a valid language there, right? A valid language meaning valid.
We can speak it, right? We can say that this is it.
If you think of it in language as an English language, but this is a mathematical language. So English language is a language, but mathematical language can be something else also. From L can here in the knapsack setting, L can be set of all instances of knapsack which has maximum value is more than t kind of stuff. Okay. So I mean the terminology comes from the linguistics world, but actually we are going to use it for mathematical things. So any problem is represented as a language.
Sir.
Yeah.
Sir, when you say verifying, so
Yes.
basically a person who is verifying is also for all x belonging to 0, 1 star. He has to assert whether that x belongs to L or not.
He has to assert. I mean, he doesn't have to find either proof
Yes.
for himself.
He does not have to find this A.
Yeah.
Okay.
Yeah.
A is given.
Yeah. So these are like.
Confused. Okay, I will read a little. Wait, sir.
Okay, I will also explain how the verification part will take you some time to digest. Okay. And I did not tell you something important, which I intentionally skipped. We'll come to that later on. Okay, but at least, so don't worry about these things. Okay, so I will go over it from the beginning in the next class and do all of this stuff. Okay,
Sure.
so next, yeah.
The job of a solver is to figure out a script A or show that there exists an algorithm.
The design an algorithm.
So the whole process of determining such a script A is what a solver has to do, and the verifier only has to take A and evaluate AX, L, right?
Correct. Whether he has outputted correctly. Yeah.
Okay. Right. Okay, sir.
Okay. Yeah. Okay, I think I will stop here today. We will talk about it in next class. By the way, I think Manasvi has already posted a couple of problems in the classroom, which are on DP. So please try to solve them before that class. Okay, try to think about them so that for the tutorial tomorrow, so that, I mean, as you can see that unless you start thinking more and more on this DP world, you will not be able to get it. But it is kind of a very natural way of solving problems. Okay.
Yes, sir. And sir, tomorrow's tutorial will be at 5, right?
Oh, at 5, right? So did you guys? Sorry. So, okay, I should like call up Manasvi and tell him that. Okay.
And on Tuesday, shall we have an offline class by any chance?
I will let you know, but I will most likely not. I will let you know. Okay. Yeah. Okay. So yeah. So see you on.
Thank you, sir. Yes, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank
Thank
you,
you,
sir.
sir.